We're going to be discussing what are sometimes called exclusive and exceptive propositions, and we're going to think about these two different general forms of propositions in the language of predicate logic. So first off, we have exclusive propositions, and these propositions, generally speaking, contain words like only or alone, or it might have a phrase like no, ... except. Hence we have a predicate, but this predicate only exclusively belongs to this one individual, for example. And then we have our exceptive propositions, and these contain phrases like all except, or save for, or a word like excluding. So with an exceptive proposition, the predicate belongs to everyone except that one guy, or everything except that one city, or that one town, or that one building, whatever the case happens to be. Now, as I said, in this video the goal is to think of such propositions in predicate logic. But to do that, we actually must think about the equivalency of individuals. We need the notion of logical identity. So this is very important, because if we're going to make universal affirmative propositions that say only that one guy has this attribute, where we have a universal quantifier, so for all x, we're going to have to specify that x equals that one guy. Or alternatively, if we have an exceptive proposition and it says that everyone has this particular predicate except that one girl over there, we're going to have to say x does not equal that one girl over there. But by the way, when we're thinking about identity, we have, so to speak, an equivalency in the absolute sense. And this, from a theoretical perspective, is very different than how two propositions can be equivalent to each other. Because two things can be truth functionally equivalent, but have very different meanings from each other in propositional logic or predicate logic. And that's actually sometimes why I hesitate to use the word equivalency. But here, when we're using identity, the equivalency is absolute. Because if x is identical to Socrates, x just is Socrates, period, end of story. Socrates is Socrates. So technically, logicians would say that identity has three main features. Reflexivity is one feature. Another one is symmetry. And a third one is transitivity. Transitivity, or the transitive principle. So with the reflexivity principle, or just the principle of being reflexive, all we have here is that something is always equivalent to itself. It's as simple as that. So x is identical to x. Whereas in symmetry, we have something like if x is equivalent to y, then y is equivalent to x. So if x is equivalent to y, y is equivalent to x. There's a symmetry there. And then we have the transitive principle, or transitivity. And here we have if x is equivalent to y and y is equivalent to z, then it must be that x is equivalent to z. Why is this important? Because if we're going to use identity in a proposition, that identity must obey, so to speak, these three features. The identity must be reflexive, symmetric, transitive. Otherwise, in predicate logic, this is not going to work. But let's think about some concrete examples and move away from this theoretical aspect, at least for now. Our first example is the following. Only God is omnipotent. So we have that key word there, only. So this is definitely an exclusive proposition. So how should we translate that into the language of predicate logic? We couldn't just do this. We couldn't just say capital O lowercase g. All that says is that God is omnipotent. So just using our standard rules of predicate logic, our standard conventions, so we have the capital O for the predicate, omnipotent, and the lowercase g, God. That's the subject here. The predicate is about the subject. But we want to say only God is omnipotent. So we're going to have a universal affirmative proposition, so to speak. So let's now say, and for all x, if x is omnipotent, then x is identical to God. And now we have something that's exclusive. So we first said that God is omnipotent, and then, and for all x, if x is omnipotent, then x is God. X is identical to God. So if x is omnipotent, whatever x is going to be, it's going to be God. So the predicate of being omnipotent belongs to God and nothing else. In other words, God is omnipotent, and for all that is omnipotent is identical to God. So this is a very good, so to speak, translation into predicate logic. And it also makes sense, I think. Alternatively, by the way, we could express this a little differently. Let's try this. Let's say capital O, lowercase g, and for all x, if x is not identical to God, then it is not the case that x is omnipotent. So that's another way to say it. And that also makes sense. So we first have our one-place predicate, our simple starting point that just God is omnipotent, and then we, so to speak, address the feature of exclusivity. And we say for all x, if x is not identical to God, then that x is not omnipotent. Let's try another example. In this example, we have all the philosophers are logicians except Jocks, who is a sophist. So this time with that except, we have an exceptive proposition. So how should we get that into predicate logic? So all the philosophers are logicians except Jocks, who is a sophist. This is a universal affirmative proposition. So we'll begin with our quantified variable, so to speak. We're talking about all philosophers. So for all x, but we're going to have to restrict this. All the philosophers are logicians except that one guy over there, who, by the way, is a sophist. So in the antecedent, we will announce x is not Jocks, and we'll say that x is a philosopher. So if that's the case, then in the consequent, we'll say that x is indeed a logician, and then we'll add our fact that Jocks is a sophist. So we have, for all x, if then, so if x is not Jocks and x is a philosopher, then x is a logician, and as we said, Jocks happens to be a sophist. So not too bad. Let's try a few more trickier examples. This time we have the only professors who had common sense were Jordan and Michael. The only. So we definitely have an exclusive proposition. But this time, note that we have two individuals, Jordan and Michael. And that's perfectly fine. We can have exclusive propositions like that. So here, I think the first thing we should do is to start out with our simple one-place predicates. Okay? And then we'll deal with for all x such and such, right? So what do we know? We know that Jordan is a professor. We know that Jordan has common sense. We also know that Michael's a professor, and that Michael has common sense. So let's just say that. So capital P, our predicate, lowercase j, Jordan is a professor. And Michael is a professor. So capital P, lowercase m. And we know that Jordan has common sense. So capital C, lowercase j. And we know that Michael has common sense. So capital C, lowercase m. And now we can deal with that exclusivity feature. So we'll say and for all x. So what's in that antecedent? Well, we know that x must be a professor and x must have common sense. So capital P, lowercase x, and capital C, lowercase x. What's in the consequent? There are only two people, or two x's, that we can get, either Jordan or Michael. So we'll say that x is equal to Jordan or x is equal to Michael. And then or, of course, is an inclusive or, so both can be the case, right? All right. So we have Jordan is a professor, and Michael is a professor, and Jordan has common sense, and Michael has common sense, and here's the exclusivity. For all x, we have our antecedent, we have our consequent. In the antecedent, if x is a professor and x has common sense, then either x is Jordan or x is Michael. In our next example, we have all planets except Mercury and Venus have moons. This is an exceptive proposition. Just like before, let's state our basic facts, and then we'll deal with that quantified variable x, where we can make an exceptive proposition. So we know that Mercury is a planet. We know that Venus is a planet. We also know that Mercury does not have a moon, and that Venus does not have a moon. So we'll say that capital P is our predicate planet, lowercase m, Mercury. So Mercury is a planet, and Venus is a planet. And it is not the case that Mercury has a moon, and it is not the case that Venus has a moon. But now we want that exceptive part, so we'll say and for all x. So what's in that antecedent? So x must be a planet, so capital P, lowercase x. We also know here, because this is an exceptive proposition, that x cannot be Mercury. And I'm not going to have room here. I'll just write down here. And x cannot be Venus. And then we get our consequent. Then, in fact, x will have a moon. So we have Mercury is a planet, and Venus is a planet, and Mercury does not have a moon, and Venus does not have a moon, and for all x, if, here's the antecedent, if x is a planet, and x is not Mercury, and x is not Venus, then x has a moon. Let's try our last example. Martha is delighted to see any grandchild other than Jennifer. So she's happy, she's delighted for any grandchild other than Jennifer. We really have two relational predicates here, because on the one hand we have to see, so we have Martha seeing someone, and grandchild is also really going to be a relational predicate, because we're thinking about a grandchild of Martha in particular, not just any grandchild out there in the world, so to speak. So we'll symbolize this as follows. Let's say for all x, so our antecedent, we'll have to say that x is a grandchild of Martha, so capital G, lowercase x, lowercase m, and we want to say Martha sees x, so capital S, lowercase m, lowercase x, So we have this other than Jennifer. So it cannot be Jennifer. So and X cannot be Jennifer. X is not identical to Jennifer. So that's our antecedent. And then we have our consequent, Martha is delighted. So capital D, lowercase m. So we have for all X, our antecedent, our consequent, if X is a grandchild of Martha and Martha sees X and X is not Jennifer, then Martha is delighted. So this is our overview of exclusive and exceptive propositions. I hope this video is helpful to you. Thank you for watching and good luck.